So shall I go ahead?
Yeah, no, let's. Yeah, so hello all. Welcome to the second edition of Bhumandal Talk Series. Today we have with us Professor Ravi Nanjundiah, who is the Director of Indian Institute of Tropical Meteorology, Pune, giving us a talk on understanding and predicting the monsoons. I would request Professor Saroj Meher to introduce the speaker.
Yeah,
Thank
yeah,
you.
yeah. Good evening, everyone. Uh, on behalf of GRSS chapter, I am welcoming Professor Ravi S. Nanjundiah for his talk on understanding and predicting the monsoons. So let me go through his biography. Professor Ravi Nanjundiah has worked on monsoons and its variability. His interests include the study of monsoons, application of HPC to climate models, use of AI ML to climate studies. He is currently the director of the Indian Institute of Tropical Meteorology, Pune, since 2017. He is the mission director of the Monsoon mission under the Government of India. He is a fellow of Indian Academy of Sciences and Indian Meteorological Society, adjunct professor of EIFR and professor at Center of Atmospheric and Oceanic Science and Devecha Center for Climate Change, IIC Bangalore. He did his PhD in Atmospheric Science and ME in Mechanical Engineering from IIC Bangalore and B Mechanical Engineering from Rani Guwahati University, Jabalpur, Madhya Pradesh. He worked as a postdoctoral fellow at the Mathematics and Computer Science Division of Arizona National Laboratory, USA. His work on the application of parallel computing to climate modeling was the first of its kind in the country and one of the first few in the world during 1980. He has been awarded the NVIDIA Innovations Award in 2013 for use of grid computing to climate modeling and the C.V. Raman Young Scientist Award in the field of earth sciences by the government of Karnataka. He has guided around 15 PhD scholars and 10 master's theses and published around 90 peer-reviewed publications. Thank you, Dr. Ravi S. Nanjo, for accepting our invitations and agreeing for a talk on understanding and predicting the monsoon. I think you can take the stage and you can start the talk.
Okay. Thank you, Professor Saroj, and thanks to all the organizers, especially Dr. Jaya, for giving me this opportunity to talk about understanding and predicting the monsoons. Monsoons, I think every Indian, come the month of summer, we start eagerly looking for the monsoons. So it is not surprising that all of us are interested in knowing about monsoons. And of course, we would like to know how good the monsoon is going to be because it kind lifeline for our country. So this is the outline of my talk. I'll give an overview of the Indian monsoon and see it as a part of the global picture and look at its various aspects because monsoon is a multi-scale system starting from very small clouds to the planetary scale, and all of them are linked together and interact with each other in a dynamic fashion. So just get an overview of the mean monsoon and how the monsoon looks like at different scales. Then I will talk about how we model weather and climate, and then how we predict the monsoons and the forecast for this particular year. And finally, I'll briefly touch upon using AI and ML for weather and climate studies. So this is the picture of the new mean monsoon, and I think all of you are familiar with it. We get very high rainfall over the northern parts of Bay of Bengal and also in central part of India and of course the Western Ghats. Interestingly, just a little distance away from it, we have one of the lowest rainfall areas, which is over Tamil Nadu and Sri Lanka. And what is interesting is if you compare, go along the same latitude, that's around about 28 to 30 degrees north, you will find that you have one of the wettest regions, that is in Meghalaya, Cherrapunji and Manaswam. And at the same latitude, if you go to Saudi Arabia, you find that there is very little rainfall there, which is one of the driest places in the world. So it's basically the uniqueness of the monsoon is also because of the fact that we have very high mountains over there's the Himalayas, which play a very important role in kind of modulating our monsoon and causing the Indian summer monsoon. And so does the Western Ghats and the mountains of Myanmar, which kind of create a lot of high rainfall. And actually, this picture about the monsoon, we came to know the full picture only when the satellites started coming in and giving us valuable data. Before that, most of our understanding was about the rainfall over the land region. We didn't have any idea, or not much of an idea, I would say, about what's happening over oceans. And it's thanks to the satellites, which told us that, okay, there is a secondary rainfall belt here in the Equatorial Indian Ocean, and also the high rainfall that occurs over parts of northern Bay of Bengal. So this is a boon, you could say, from remote sensing and satellites. We always thought of monsoons as a kind of a giant sea breeze. And we thought that the land heats up and then you have monsoons coming in. And the hotter the land, the stronger the monsoon. But actually, if you look at the correlation between land surface temperatures over India and that joining, we find that there is a negative correlation, which means that if the land is very hot, then the monsoon is weaker. Only during the early part of the monsoon, perhaps in early June, does the hot land play a role. But once monsoon starts, then it has its own dynamics. There is a lot of cloudiness, and these clouds, when the water vapor, which is carried from the adjoining oceans, it kind of condenses, it gives heat to the atmosphere, and that drives you could say, the engine of the Indian summer monsoon. So only during the initial part, we could say that there is a role for the land-sea contrast. But then afterwards, the dynamics take over. And if we want to see the monsoons, is it a local or a global system? That's what we would like to know. And if this is again thanks to satellites, we see that this is the kind of rainfall and cloudiness which we get. The top picture is from the month of January, when the rain belt, the high rainfall region, is much to the south of India, and there's hardly any rain over India. And then when you come to the month of July, you find that there is a lot of rain in July over India, and it's part of a global system. This global system is called as the ITCZ, which is the Intertropical Convergence Zone. And also, our Indian summer monsoon is also part of the Asian monsoon, which is again embedded within the Intertropical Convergence Zone. So as I said, it's a multi-scale system. You have clouds that are very small scale. The rain that you are getting at any place at this moment, it's kind of raining very heavily in Pune today. And that is kind of embedded into a larger scale system, which could be a mesoscale system. And then that could be embedded in a larger scale, which we call as depressions, which would be part of the Indian summer monsoon system, which in turn is part of the ITCZ. So there are multi-scales which are occurring simultaneously and interacting with each other. It's not that there's only a one-way interaction. These small clouds are where all the energy is being produced for the monsoons to occur. That is the heating, because of the latent heat release. When water vapor changes to liquid, a lot of heat is released, and that heat kind of drives the monsoon. So that happens at the smallest scales. But then that drives the entire monsoon system, which in turn plays a role in changing the circulation, because that changes the pressure gradients in the atmosphere, which drives the flow, and that kind of becomes a kind of a part of the global system. So this kind of a two-way interaction is what makes monsoons so challenging and interesting to study and to predict. So if you look at the surface winds, we find that in the month of January, most of the winds over India, this is India here, and are away from land into the ocean. And this is where we have convergence of winds, which we call as the intertropical convergence zone. And when we move to July, the picture is very different. You have winds crossing across the tropics, that is the equator, and moving into land. And this moisture-laden winds are kind of important as far as monsoon is concerned. So, and there is a change in wind, and that's what the name monsoon came from, the word Mausam, which basically means seasons or change of seasons. And that was kind of observed by the ancient mariners, and they gave the name monsoons, which came from the word Mausam. So if you look at the typical positions of ITCZ, the lower one is the one in January, and the red one is the one in July. And what I would like you to notice is that the maximum excursion of the ITCZ occurs over the Indian region, or in all other places, let's say in Africa or in America, there's hardly any movement. But when it comes to the Asian, especially the Indian monsoon region, the ITCZ moves from well south of the equator to its mean position over the Indian region. And this ITCZ, when it visits us during the summer months, is what causes our monsoon. And it's basically a north, what we are looking at is a north-south circulation, where there is a lot of rising motion here. This rising motion takes moisture from the lower levels into the upper parts of the atmosphere, where the water condenses and rains out to give us the monsoonal rainfall. And now coming into the picture of the monsoon, we all always eagerly await the onset of monsoons. Monsoon onset occurs especially, let's say, over around late May to early June. The earliest one occurs over Andaman Nicobar, which is around 22nd of May. And also at the same time, Thailand also has its monsoonal onset. Then it kind of slowly progresses into India. And around 1st of June, we have the onset over Kerala, which is always eagerly awaited. And there is a lot of speculation and discussion about what the onset is likely to be and how good the monsoon is. And slowly it progresses northward. And in Karnataka, we get it around 5th of June. And then it moves to Mumbai around 10th of June. And slowly it progresses. By the end of June, early December, early July, it kind of moves into Delhi. And then finally, at the end, by the second week of July, we have it covering over the entire country. So this is how the onset occurs. It's a kind of a progression, but it is not necessary that every year there will be this uniform progression. Some years, the onset occurs earlier in the northern parts, some parts of the northern, let's say in Karnataka and parts of Maharashtra, and then it occurs at other places. So this is only a mean picture that we talk of, but it's not always necessary that it occurs during the same thing. So this is a typical picture of what could be for the onset of the monsoon. If you look at the early part of the monsoon, most of the rain occurs only in the southern parts in May. Very little rainfall actually occurs over the mainland India. And then in June, it kind of progresses and you get a lot of rain during over the western coast and also parts of the northern Bay of Bengal. Northern parts such as Punjab and Rajasthan still do not get much of rainfall. Now, if we look at the peak monsoon period, right now we are in the peak monsoon period of July and August. We get a lot of rain in what we call the core monsoon zone. That is consisting of the states of Madhya Pradesh, Chhattisgarh, Uttar Pradesh, Haryana, etc. And of course, Delhi. So though all these regions, they get a lot of rain during the months of July and August. And of course, there's a very high rainfall region along the Myanmar coast, which is due to the Myanmar mountains and also along the western Ghats. So you can also see a secondary rain band over equatorial Indian Ocean, which is also prominent. And what I would like to mention is that there is a sharp gradient of rainfall. There's very high rainfall along the western coast. And as you go slightly westward, you find that the rainfall is almost, it's just isn't there. And there's an interesting reason. That is, we'll come to it in a moment, but what I would like to point out is that the sea surface here is very cold, partly because of the high winds that come from here, and also because there is cold water coming from below the surface, which kind of cools the surface here, and thus it is not able to sustain cloudiness and rainfall. And that causes it to be almost like a watery desert. You have, of course, the sea, but you don't have much rainfall happening during the months of the July and August. You can see a similar picture for August, very similar. And also, we see this low rainfall region over Tamil Nadu and Sri Lanka, which is partly caused by the mountains and also by the prevailing oceanic conditions there. And we come to the third part of the monsoon, which is the withdrawal phase, that is during the months of September and October. We find that monsoon while it is widespread over mainland India, it's kind of has decreased, and it's kind of the high rainfall regions are kind of confined to northern parts of Bay of Bengal and adjoining northeastern part of India and eastern part of India, and of course a little rainfall over the western parts. Coming to the month of October, we find that this scene dramatically changes, and we get rain in Tamil Nadu, which up till then had very little rainfall, and also parts of Kerala and southern parts. Essentially, the rain band kind of stays near the southern peninsular region, and very little rain occurs over the northern parts of India. We know that monsoon, it's not necessary that it rains equally on every day during the 120 days of monsoon, that is from 1st of June to 30th of September. That is what we call as the monsoon season. We have times when it rains very heavily, and also periods when it kind of rains very little. And this, what looks like a one-day scorecard, also with peaks and troughs, basically shows the days when there is high rainfall. 1975 was a year when the rainfall was very high, and this is for 2002, the year when the rainfall was, it was a drought year, one of the strongest droughts that we had. And what we see is that there are many such peaks during a strong monsoon year or an excess monsoon year, and fewer of them during the monsoon when it is weaker. So these spells, when the monsoon is weak, is called as a break spell, and when it is strong, these are called as the active spells. And for example, this, even though it was a drought year, we did have a strong spell of rainfall, and that is called as an active spell. And when it is kind of weak, it is called as the weak or the break spell. And if you look at rainfall, it is kind of limited to parts of northeast India. And this is a active spell picture where you have high rainfall over central Indian region and also parts of western Ghats, and of course parts of North India, and of course other parts such as Tamil Nadu and adjoining arid regions where you get very little rainfall during an active spell. And during a break spell, most of the rain occurs over southern part of peninsula and also during the northeastern region. So they kind of go in opposite sense to the rest of India as far as rainfall is concerned. And so if we want to look at monsoons, we find that if you have, as we saw, if you have longer active spells, the monsoon is likely to be stronger. And if there are longer weak spells or the break spells, then the monsoon is likely to be a drought. And if you ask ourselves, how does the rainfall vary in space and time within a season? We come to what is called as an intra-seasonal variations. We find that within a season, if we look at the movement of the cloud bands, again, this information we got from satellites, that they kind of start somewhere around south of the equator, around 5 degrees south or 10 degrees south of equator, and then they move northward and kind of culminate over the monsoon trough region, which approximates to, let's say, MP and UP and Bihar in that region. And then about 30 to 40 days later, another system forms and kind of propagates northward and again culminates over the northern region. So this kind of a movement of the cloud bands is kind of typical only to the Indian summer monsoon and not to the other parts of the world. So that's makes more interesting. And sometimes break spells can be broken by these northward movements, and they can cause a lot of rainfall. And not only they cause rainfall, but they also create conditions which are conducive for low pressure systems to form, and that they can further give us a lot of rain. So actually how these poleward propagations occur is still a matter of research, but they do play a role, as I said, in reviving active spells after a break spell. So during, we also, going to a smaller scale, we looked at the mean picture, then we looked at longest periods like active and break spells. Then we started looking at even smaller scales, which was the northward propagation. Now we look at even smaller scales, which is called as the synoptic scale, where we are looking at lows and depressions. These are low pressure cyclonic systems which form and propagate. Most of them during the monsoon occur over the northern Bay of Bengal, and they move northwestwards into the Indian region, and these cause a lot of rainfall. And what we find is that there are many more such lows and depressions which form and propagate during an active phase, and far fewer of them, and very few of them which happen to come into the Indian region, which occur over northern part of Bay of Bengal and then move northward. Very few of them happen during the break spell. And if we see, they are more, as I said, they are very short-lived systems of a few days, but they give substantial amount of rainfall. And even though the ocean is very conducive for cyclonic activity, there is what we call as a very strong vertical shear of the wind. That is, in the lower levels, we get winds from the west, and at the upper level, the winds are from the east. So this kind of shears off any vorticity that could form, and we could become a cyclones, which is why just after once the monsoon has kind of withdrawn, even when the ocean is still warm, we get a lot of cyclones during the post-monsoon season or in the pre-monsoon seasons, but we never get any cyclones. Very, very seldom we get a cyclone within the monsoon season. That's because of the wind structure that happens over the Indian region. Now coming to variability from year to year, we have certain years when there is hardly any rainfall over India. This is the picture of rainfall happening. The blues indicate very low rainfall and the reds indicate high rainfall. This is for July 2002, which was one of the strongest droughts on record. And this is for a near normal year, on the year of 2003. You can see that there was a lot more rainfall over mainland India in 2003 July as compared to 2002 July. So basically, this is the variability from year to year, and there are many reasons for this variability to occur from year to year. And this is a kind of a picture of the recorded history of monsoons starting from 1870 to almost now. And actually, India has one of the best rainfall records in the world. And very few countries have rainfall records dating back to the mid 19th century. And what we will see is that there are periods when monsoon is very strong, and then also periods when the monsoon is very weak. And these tend to get clustered over a period. This is called as the decadal variability. Here we had lots of weak rainfall seasons or many droughts in this period. Then again, if we move to this period, there were very few droughts. And then again, from the 60s, we had very more droughts. And then again, now it appears that if you look at the more recent data, that there are fewer droughts happening. So if we look at some of the droughts were related to things which happened over the rest of the country and or rest of the world. And one of the things that modulates, we could say, the Indian summer monsoon is the El Nino. That if this is a picture where we are looking at both El Nino and the Indian summer monsoon, we note that there are a few droughts which are related to the occurrence of El Nino. Some of the excess rainfall are associated with the opposite of its kind, what's called as La Nina. I'll come to in a moment what is El Nino and La Nina. This is basically a change in the circulation and rainfall pattern over the central equatorial Pacific. And we find that there is a strong relationship between El Nino Southern Oscillation, ENSO as it's called, and the Indian summer monsoon. It's about 0.53, which in meteorology is a very high correlation, which may look as a very low correlation to the rest of us. But in meteorology and in climate, such a correlation is hard to get, and it's considered to be very high. And occurrence of ENSO disrupts what we call as the Walker circulation. I'll come to that in a moment, which in turn modifies the Hadley cell. Hadley cell is the kind of a circulation which happens in the north-south direction with rising motion over the ITCZ region, that is our, let's say, the monsoon region, and descend over the mid-latitude desert. This is kind of disrupted by the changes in the east-west circulation, which we call as the Walker circulation. So let's look at what is an El Nino and what is the Walker circulation. So this is the picture of the vertical velocities for during the month of January, and this is the picture of vertical velocity during the month of July. The blues indicate rising motion, and reds and yellows indicate descent. So what we find in January is that most of the ascent is occurring in near the equator and or south of the equator, which is also where the position of ITCZ was. The air rises here and descends elsewhere, which kind of causes the rain to be very low there because you have air from upper levels coming down, which is kind of dries out as it comes to lower and lower levels. On the other hand, when we come to July, we have rising motion over the Indian region and also adjoining parts of Indonesia. And that kind of is where the Hadley cell's ascending cell is, or the Hadley cell's rising limb is. And the descent is all over these regions, which are nothing but the mid-latitude deserts, which is where all air is always descending. So there is very little rainfall in these regions, especially Saudi Arabia and the adjoining regions of north of Tibet into China and all, where we have most of the deserts, including, and of course, in Africa over Sahara, and in the Americas, we also have a desert in the mid-latitude. So that's because of the Hadley cell where you have descent into this of air, which is kind of rising over, let's say, near the equator and descending there. And if you look at in the east-west direction, we have very strong ascent happening over Indonesia and descent happening over parts of the coast of the Americas. So this is what we call as the east-west circulation, is where you have a rising motion happening here, kind of moves towards the east and descends here. So this kind of a circulation is what we call as the Walker circulation, named after Sir Gilbert Walker, who was the first Director General of the Indian Meteorological Department, and who was one of the first to kind of ascertain that there is a relationship between ENSO and the Indian summer monsoon. It was a path-breaking work and kind of helped us to do our monsoon predictions in a better fashion and also improve the understanding of the Indian summer monsoon. So this is another picture of the Walker circulation, which is where you have rain happening over Indonesia. So you have this rising motion and a lot of cloudiness there. It travels eastwards, descends along the coast of Americas, and then again returns. So this kind of a circulation is this is called as a Walker circulation, and this is the normal pattern of Walker circulation. Some years, for some reason, which we completely do not understand and we'll come to in a moment, we have this massive high rainfall region moving into central Pacific, which is what causes an El Nino. And then it kind of disrupts the entire east-west circulation. And related to that is the north-south circulation that also gets disrupted. And that influences our Indian summer monsoon. So if we look at the question of why, what causes this rainfall, much higher rainfall, we are after all looking at equator where it should be very hot, and the amount of solar radiation that we are going to get is about the same everywhere. The fact is that you have very warm oceans off the coast of Indonesia and very cold oceans occurring off the coast of the Americas. So if the ocean is very cold, then it kind of cannot sustain cloudiness and rainfall. But if it is warm, it can kind of sustain it. And this kind of leads to an asymmetry in the east-west direction, which kind of sustains the Walker circulation. This is a picture of the relationship between rainfall and the sea surface temperature. What I would like to point out is still about 26 to 27 degrees. The rainfall is very low. The x-axis is the sea surface temperature, and the y-axis is the rainfall. So as we go from about 24, when there is hardly any rainfall, to about 27, there is some more rainfall. But after 27 degrees centigrade or 27.5 degrees, it shoots up very sharply and flattens out around 30 degrees centigrade. So this is where, and if you look at the sea surface temperatures, here it is much above the threshold of 27 degrees centigrade. And here it is much below, it's around 23 to 24. So that it cannot sustain clouding and rainfall here, but it can sustain clouding and rainfall here. So you have ascent, you have clouds, which kind of cause rainfall, and then the air moves in this direction because of the pressure gradients, then descends here, and you have this Walker circulation. That's because of the asymmetry between the western part of Pacific Ocean and the eastern part of Pacific Ocean, which causes the rainfall. And that's related to sea surface temperatures. And if we look at it, now we know that, okay, ocean plays a role in Walker circulation and also in our monsoons, and also it is affecting the atmosphere. So if you look at Walker circulation, or it's basically a coupled system. You have warm ocean to the west and cold ocean to the south. And that's also related to what's happens beneath the beneath the surface. The colder air, water in the eastern part is much comes closer to the surface, so it can easily be brought to the surface, and the winds are such that they kind of facilitate this cold water to come from below the surface, what we call as a thermocline, into the upper parts and then cool it, while here it is much thicker, so it is more difficult for the colder lower part of the ocean to come up and cool the surface, and hence this stays warm and this stays cold, and that kind of sustains the Walker circulation. So it's basically a coupled system, a coupling between ocean and atmosphere, which drives this east-west circulation. So this is another picture of that, and we also have, we call as a Southern Oscillation Index. So certain times we have higher pressure here most of the time and lower pressure here, and sometimes this kind of fluctuates. So that is called as the Southern Oscillation Index. And if we look at the Southern Oscillation Index over a period of time, we find that there are epochs when it is positive and cool when it is cool, and sometimes it's negative when it is in the El Nino kind of a situation. So positive values indicate strong Walker circulation, while negative values indicate weaker circulation. And this Southern Oscillation, which occurs between the eastern and western parts of the Pacific Ocean, is quasi-periodic. That there is no clear periodicity, but occurs between about, let's say, 3 to 8 years. And whenever it's in the Southern Oscillation Index is negative, it coincides with what we call as the El Nino. And when it is positive, it is coincides with the El Nino. So, as we discussed previously, what causes this Walker circulation to weaken? As I said, most of the time, the clouding was along the coast of Indonesia, but sometimes it moves into Central Pacific. And that's because there are many theories on why this happens. One of them is that the low-level winds which blow from the west, they kind of weaken. And on what we call as the intra-seasonal scale, that is on a period of about 30 to 60 days, there are bursts of the wind which kind of weaken. And then, so if you look at the mean pattern, they are kind of in this direction. That means the wind is always from the east at the lower level. But sometimes this kind of weakens. And then once it weakens, the sea surface becomes warm. And then it helps to kind of allows clouds to form. And when this occurs, and it happens in a sustained fashion with more clouding over the Central Pacific, that's what we call as a El Nino kind of a situation. So if we look at the relationship between ENSO and ISMR, we find that quite a few of the strong droughts that occurred within the occurrence of a El Nino. And quite a few of the strong monsoon years also happened in occurrence with the opposite phase of it, that is where the La Nina. That is when there's very strong ascending motion of the Indonesian coast. And some of these droughts occurred when there was very strong ascending motion in Central Pacific, which was an ENSO kind of thing. So this is one of the players, but we also know if you look at a scatter plot between ENSO index and this is on the x-axis, we have the ENSO index. On the y-axis, we have the strength of the Indian summer monsoon rainfall. We find that there are some outliers. If it was always related only to ENSO, we should have a strong monsoon, weak monsoon here, monsoon years here, and strong monsoon years here. But then we also find outliers. It certainly means that ENSO is not the only player which kind of dictates the variability of our monsoon from year to year. And that is what we are still looking at. One of them is what happens over Indian Ocean. As I previously said, we have a lot of rainfall happening over this equatorial Indian Ocean, but that is also not the uniform over the entire equatorial Indian Ocean. There are periods when there is more clouding on the western part of Indian Ocean and less clouding on the eastern part. This we call as a positive dipole, or its equivalent in that atmosphere, which we call as the Equatorial Indian Ocean Oscillation, or EQO for short. And it's again a coupled event. And in years when there is higher rainfall on the western part, we find that there is more clouding and rainfall over the Indian region. And the opposite happens when we have a negative dipole or a negative equino, when there is more clouding off the Indonesian coast and less cloud. So that kind of weakens our Indian summer monsoon system. And there again, if you look at the droughts and the teleconnections, where we look at both the Indian Ocean and so, then we find that all the major extreme events, whether strong or weak, can be explained if we look at a kind of a phase space of equino and so. And when both of them are favorable, we get very good monsoons. When either of them is unfavorable, then we could have a weaker monsoon. So, and even in years when ENSO was strong, unfavorable, like for example in 1997, but equino was favorable, the monsoon was near normal. And in 1994, when the ENSO was near normal and equino was favorable, we got an excess monsoon year. The numbers are all here, and you can see that some of them which had very high rainfall occurred when equino was positive, and so was ENSO. So in this diagram, you can see the extreme high rainfall and the droughts. Certainly, when both of them are unfavorable, that's where you see the clustering of droughts in this region. And of course, the near normal monsoons, there are many other players which could be affecting it, which is like within plus or minus 5% of the monsoon. That's more difficult to talk about. And the exact mechanism, how the linkages work, is still a matter of research. So that was kind of a bird's eye view of the monsoon. We started from the mean monsoon, looked at how it fluctuates within the season, and then embedded in that were lows and depressions, and followed by what happens from year to year, and the players which kind of modulate the strength of monsoons. We found two of them, that is ENSO as well as equino. Now, if we were to study with models, we need to ask ourselves, how do we model weather and climate? We have seen that monsoons are part of the global climate system and are dependent on atmosphere, ocean, and land conditions. And if we look at weather and climate, atmosphere, ocean, and land conditions evolve interactively. That is, what happens in the atmosphere can change what's happening in over the ocean and also with land, especially over land. If it starts raining very much, we have a high amount of moisture, and also the temperatures are likely to be lower. While over ocean, high winds, which driven by high winds, kind of cause the sea surface temperatures to be lower because of higher evaporation due to high winds. And if you were to model and predict monsoons, we need a model that encompasses all the components that give rise to weather and climate. So before we kind of start looking at the actual models of what is the predictions and how we do the predictions, let's look at the different components and their interactions. We know that climate at a place is affected by the conditions of the atmosphere and land and ocean there. We also know that the conditions at the surface, if it is ocean or near or on land, if it is a mountain, or if it is bare land or desert, or if it is a forest covered grassland, all of that impacts the climate of a place, or climate, and also the weather of a place. So we need to understand how these features interact with each other, and putting these together and understanding climate using numerical techniques is what we call as climate model. So if you look at a big picture where all of these interact, this is how it looks like. You have we have atmosphere here, ocean here, and land here, and they all interact with each other. We have basic source of moisture is from the oceans. if it rises and then it kind of rains here, then if there is a mountain there, and if the mountain is very tall, we may get the precipitation in the form of snow, which might form into ice, which in turn can form glaciers and then kind of form rivers, which will flow into the ocean. And that would be like the hydrological cycle. And everything is kind of driven by the heat coming from the sun. And we will also have a lots of clouds over everywhere, which also kind of affects the amount of radiation coming in. So if we look at the ocean, atmosphere, land system, it is a kind of a problem in thermodynamics and fluid mechanics, and it's much more challenging because of turbulence, which is what drives all these clouds. It's a much tougher problem than mechanics if you are really looking at it, and that's what makes it much more difficult for us to predict weather and climate. There are many issues coming when, especially when we look at climate, which includes what happens by the intervention of humans, which we call as anthropogenic factors, which also come into picture. So all these components are interacting with each other. And if there's a perturbation in one of them, for example, let's say we change the land, the usage from forests to either agriculture or to urban areas of deforestation, then it is going to change it will perturb the entire system, and that is kind of likely to cause changes to the climate. And if we look at ocean and atmosphere, if you're looking at it from a modeling point of view, they are mainly composed of fluids, while land surface and sea ice would be solids. So if we look at ocean atmosphere interaction, we find that ocean forms a very important part of the climate. In high thermal, it has high thermal inertia and kind of modulates, or kind of, you could say, dampens changes in climate. It's like a flywheel. We all know that if you are in a coastal region, the temperature fluctuations are much less. For example, if you are at Mumbai, the temperature fluctuations on a day-to-day basis, or even from a season-to-season basis, is much smaller as compared to when you are much more inland. Let's say if you are in a Delhi or elsewhere, well away from the oceans. So this is the effect of oceans, that is, they kind of have a large high thermal inertia, which kind of dampens the fluctuations. It is also a major source of moisture for us, and the circulation in the ocean can also modulate climate. For example, we have the Gulf Stream off the coast of America, and also the Kuroshio off the coast of Asia. These are warm currents which kind of create conditions more conducive for us in the coast, which is why it is much more comfortable to live where there is warm currents as compared to where there are cold currents. And we also know that there's an interaction, as we saw in the case of Anso. Atmosphere drives ocean through winds, and ocean is the most important source of energy. It also heats atmosphere to sensible heat, and also what we call as long wave, which is the infrared radiation. And if you're looking at it from a climate change point of view, then we find that it also acts as a carbon sink. And land-ocean atmosphere interaction, land also, as I said, it could be rain, and then the friction from land could also affect the oceans, the atmosphere surface. And albedo of land can significantly affect our climate. Land cover can also affect the moisture between land and ocean, and through land and air, sorry, not land and ocean, and that can also have an impact. So if we look at if you are looking at how we model them, then we have to model all the four subcomponents, that is atmosphere, ocean, land, and sea ice. And we need to look at them in detail, and we need to identify the major processes that affect these components and model them. So, and some of the processes, we have to do it in an empirical fashion. For example, when we are making our model, we will not be able to resolve every cloud on the surface of the Earth, because the resolution for that would be less than 1 kilometer, and we can't run a global model with clouds that trying to model every cloud. So we abstract the important effects of these clouds and replace them what we call as a parameterization. So we look at the individual components. These are the equations. I will not bore you with the equations, but what I would like to say that air is a fluid, and for a fluid, the mass has to be conserved. Hence, we have to use conservation of mass. Air moves from place to place, so it will have velocity and momentum. So we have to use the equation of momentum conservation. Equation of state because it's a fluid, and energy of fluid has to be conserved. So we have a equation of conservation of energy, and this is what actually, and they all get coupled because if you open these total derivatives, we get advection components, that is winds driving temperature energy from one place to the other, or momentum, and then a heating from one place, difference in heating kind of causing pressure gradient. So you get a coupled the system of equations where the energetics and the mechanics kind of interact with each other. And if we are looking at the climate change scenarios, then we have to have multiple species in the atmosphere. For example, water vapor, different trace gases such as oxides of sulfur and oxides of nitrogen, and these days even aerosols, the particulate matter, which is very important for air quality. They all need to be modeled. For that, we'll have to have a species conservation equation. If you look at oceans, water is also a fluid, and hence similar equations will be used. The difference is that water is much more dense and is less compressible, and but there is also a difference in salinity. That is, we have more salt at one place, less salt at the other place in the ocean. So there are gradients because of that, which kind of change the density and hence the pressure gradient and hence this, the circulation patterns. So salinity also plays a major role in determining the circulation. However, we always make simplifying assumptions to the ocean. And one of them is that, as I said, density of water does not change. And unlike atmosphere, which is global in nature, oceans would be enclosed or semi-enclosed. And we need to consider rigid impermeable boundaries to kind of model that. And sometimes flow from rivers or high precipitation from the atmosphere needs to be considered for determining salinity. For example, over Bay of Bengal, where a large amount of river water from the Brahmaputra and Ganga flows into the northern Bay of Bengal, it kind of reduces the salinity, which in turn forms what we call as a freshwater lens. That is a thin layer of low density water sitting on top of higher density saline water. And this kind of can heat up and cool down very fast, which is one of the reasons why you can have a large number of depressions and lows forming over this northern part of Bay of Bengal. And if you go to higher latitudes, ice can form, and ice can float down and it can also melt. This also needs to be considered. And the high thermal inertia, as we have already discussed, causes the diurnal cycle, that's the fluctuation during night and day of the temperature, to reduce. However, in regions where the mixed layer is thin, as I said, diurnal or intraseasonal variations would be very significant. And if we look at land, we know that, okay, there are many interactions which happen because of transpiration from trees and evaporation from lakes, and also runoff coming as rivers and in turn going into the ocean, which again has evaporation and winds carrying in, and all these are kind of linked to each other. And hence, we need to consider that when we are modeling processes on land. And unlike oceans, its thermal inertia is very small. We can neglect the horizontal transport of heat over land. Temperatures change, have huge diurnal cycle because of low thermal inertia. And land cover changes can also cause change in climate, such as deforestation, which we have looked. And also, land can act as a sink for carbon in land ecosystems. That is, if you have lots of forests, then they act as, then the carbon is stored there. But if you remove those trees, then carbon cannot be stored, and therefore there will be more greenhouse gases in the atmosphere. So this is another picture of the complex interactions that occurs between atmosphere and land. I will not go into all the details. We also get many other chemical constituents which are emitted to the atmosphere, and land surface processes are closely linked to the atmospheric boundary layer. That is the lowest part of the atmosphere. And the kind of models that we use can vary in the degree of complexity. The simplest is where we use it in the form of a bucket where rain falls in, and then it kind of flows out when it is full. But then there are many more other kind of models which also take into account what's happening to the ecosystem, and those are called as the vegetation models. I will not go into the details of that. And if you look at the fourth component that we talked of, the model sea ice, we find that sea ice, as you can see, is not again continuous. So, but sometimes on the larger scales, we need to make assumption of continuum. We parameterize again, as we did for clouds, the sea ice thickness on subgrid scales. And the major equations that we use is the equation for ice thickness, equation for conservation of momentum, equation of enthalpy, and heat equation in ice and sea. So if we look at how we discretize these equations, we have seen that they consist of solving nonlinear coupled partial differential equations. So we use various methods to solve the equations. For the atmosphere, we discretize it either using finite difference or finite volume methods. And if you are using a global model, then we can use what's called as a spectral method. That is, we decompose atmospheric motion into two-dimensional waves in the north-south and east-west directions. For oceans, we generally use finite difference and finite volume techniques. For land and sea ice, generally the finite differencing techniques are used. We may also make certain approximations. If the model is coarse resolution, let's say of the order of 100 kilometers resolution, that is distance between two grid points is about 100 kilometers, we assume a hydrostatic motion that in the vertical. That the advantage is that we can remove the sound waves which carry very little energy, and hence we can take largest time steps. And when we are running these models for hundreds of years to understand motion, to understand climate change, then making a larger time step makes it very computationally efficient. So if we look at what is the difference between weather, modeling weather and climate, climate is a long time event which occurs for more than a month to about hundreds of years. Where weather is the behavior of the coupled system for a few days. We want weather to be at a higher degree of accuracy. We would like to know whether the weather with inside, let's say, different parts of Bangalore. For example, it may rain in Electronic City, but not in Yelahanka. We would like to know when it's going to rain and what would be the amount, let's say, in either Yelahanka or in Electronic City. We need that. For what that we need to have very high spatial and temporal resolution for variation of weather. And it highly depends on the initial state that we give to the model. So it is essentially an initial value problem. Climate occurs over a longer period. We may not know all the factors that influence climate. Human behavior, especially, will change the greenhouse gas concentrations. And of course, if we have enlightened human behavior, this effect will certainly be minimized. But we do not know how the greenhouse gases concentrations will change. We can only speculate on the various scenarios, that is on whether the behavior is going to be an enlightened one or it's going to be business as usual. And that is something which we cannot crystal gaze at this moment and say that, okay, this is what is going to happen 50 or 100 years down the line. And we also do not know what kind of volcanic and natural activity could occur, which could also affect climate. For example, if you look at the little ice ages in the medieval periods, they were largely occurring because of various factors, which includes large volcanic eruptions. Especially in the early 19th century, we had the Krakatoa and others, which had a significant effect on climate. They didn't have summer for quite a few years. And there was a lot of aerosols in the atmosphere, which changed the climate, of course, on a shorter scale. And if we have to look at climate, then we have to conduct various scenarios. That is, we'll say that, okay, there is going to be more CO2 in the atmosphere or less CO2, and then run it for hundreds of years, these simulations, and study them to understand possible scenarios of climate change. So if you want to look at how we create good initial conditions for weather and climate, especially for weather, then we need especially for if you are looking at weather, we know that 2/3 of Earth is covered by water. So very difficult to get measurements of atmosphere. This is where we use satellite data. Today, most of the initial conditions, about 80% of it comes from satellites. Input data, of course, is not going to be uniform in space and time. So we need to kind of create it in such a way that it kind of goes into the model grid. And also need to control the quality of data and how it kind of can go into to the models. This process is what we call as data assimilation. There are various techniques to minimize the error which can happen in the initial conditions. Variational techniques, which is called as 4D VAR, where we kind of minimize the error in both space and time. These days, even ensemble Kalman filtering techniques are also becoming popular to create proper initial conditions. This is a matter of significant research, especially how to use satellite data very optimally and in a best manner so that we get the best possible initial conditions. And quite a bit of the improvement in weather forecasts have come because of better initial conditions, which again has happened thanks to the larger amount of data that we are getting it from the satellites. So now let's look at how we predict the monsoon. We have seen that the dynamical models are based on laws of fluid mechanics and thermodynamics, and they are widely used for predicting weather and studying climate. That is, these are models which study the state of atmosphere, land, and ocean in an interactive fashion, as we saw in the couple models. The long-term memory for a seasonal forecast, that is for about 3 seasons in advance for the entire season. For example, when we are talking about the mean monsoon, we are going to do a forecast, let's say in May, then we need the long-term memory is certainly going to come from the ocean, which has a higher thermal inertia, and its effect is going to be lasting for a longer period. So the preparation of initial conditions is very important, and we use what we call as the data simulation, which we just discussed. In India, operational seasonal prediction of monsoon using coupled models is being done using models which we have developed under the Monsoon Mission Program. Before that, we didn't have any model which could do a seasonal prediction, a dynamical model. Most of them were statistical models that were being used. And Monsoon Mission was started with the kind of aim to improve monsoon forecasts. And this was started around 2012. And the first phase was over in 2017. The second phase is now getting over in 2021. And the third phase is likely to continue for another 4 years. For monsoons, the dynamical models developed under the Monsoon Mission have perhaps the best skill in the world. And of course, we also use statistical models for doing seasonal forecasts. So this is a schematic of how we do seasonal prediction. So this is what we call the Monsoon Mission Climate Forecast model. We have the atmospheric model, which is being run at 37 kilometers. We have a land model called NOAA. We have an ice model, and all of these, and the ocean model, which is the modular ocean model. And the data for this is kind of comes from various organizations. The actual model is run at Noida. The inputs come, the atmosphere comes from NCMRW, the National Center for Medium Range Forecasting at Noida. The ocean conditions come from the Indian National Center for Ocean Information System in Hyderabad. And all of them are coupled together, and the development of the model is done at the Indian Institute of Tropical Meteorology in Pune. So it's kind of a synergistic work where all these organizations work together to improve the monsoon forecasts. And the original model with which we started came from the National Centers for Environmental Prediction in USA, but it has been considerably modified, and the resolution changed, and many other changes are being envisaged, which will kind of slowly evolve into an Indian model. So if we look at seasonal forecast, they also use statistical models in India Meteorological Department. And these are the various parameters they take into consideration to kind of create the statistical forecast. And if we come to this year's forecast, the probability of near normal is very high, and probability of low deficient and excess monsoon is also relatively smaller. So what it means is that we are likely to have a near normal monsoon. And if we look at from the dynamical models, this is the picture for June to September for India. And it shows that it's likely to be very near normal. That is, the blues mean that the rain is going to be either near normal or going to be excess. So there's a high probability of there being a good monsoon. And as we have seen up till now, monsoon has been pretty good. And also, if you look at what is happening over the Eastern Pacific and Central Pacific, where El Nino occurs, there is very little rainfall occurring there. So the predicted, so it's likely to be a very good monsoon. So if we look at the August, September, that's the remaining season of the monsoon, it's again likely to be very high. So this is the picture for the deviation of the rainfall for the month of August. It kind of shows that the rain is likely to be very high. And this is from initial conditions starting in July. That's the latest we can do for a seasonal forecast. And in September also, we find that there's going to be quite a bit of rainfall, especially over northern parts, maybe slightly lower in other parts of the country. But if in August, the rainfall is likely to be very widespread over the entire country and likely to be very high in the month of August. And in September, it could be slightly lower, but still the overall monsoon is likely to be very good. And if you look at the El Nino forecast, it's near normal, both in the earlier forecast that we got from our model in April, and also this is from July. You find that it's kind of close to zero, which means that it's neither going to be a El Nino nor going to be a La Nina. So a near normal monsoon. So near neutral conditions are likely to continue. So it's not going to really affect our monsoon. The other player that we talked of, the Indian Ocean Dipole, that also is slightly negative, but nothing major to worry about. And in April, it showed a stronger negative dipole. But what has happened actually is that it is not really developed into a very strong negative dipole, and it's still near normal. So nothing much to worry about. So both the features, that is the Indian Ocean Dipole as well as the ENSO, they are neither in an unfavorable phase, so to speak. So we are likely to have a very good monsoon. So this is the current situation of the monsoon. And you can see that there have been no major break spells that happened. And in the last few days, the rainfall has been fairly good. This was still yesterday. I mean, today also, rather day before yesterday, and today also it has been, or rather yesterday's rainfall also was above this line, which is the long-term average. And so monsoon is near normal at about, I think, 0.6% above. And this is for the 4 regions. If you look at it, the top one is for, I think, Northwest India. This is Central India, and one of them is for the peninsular region. So except, I think, for the Northwest India, which is slightly negative, but that is being made up with high rainfall in the last few days. So, and the mean itself, because it's largely a desert region, the mean rainfall is low. So one big spell of rainfall is likely to make it very positive. And northeastern and eastern and northeastern India is also near normal or slightly positive. And so is it for Peninsula and Central India. So overall, it has been fairly widespread and uniformly distributed. It's not like it's skewed that way. Some regions are having very high rainfall and others are not having rainfall. And overall, it is looking like good. So it's all over the country. We are finding the rainfall to be evenly distributed. So if you look at the next few days, we find that the rainfall is likely to be near normal and quite strong. And it is likely to be in a stronger phase over most of India. This is for the next 4 days, starting from 24-hour rainfall. This is after 48 hours, that is after 2 days, with initial conditions from yesterday. And this is for day 3, and this is for day 4. And so if we look at for the next few weeks, this is for week 1, that is starting from 13th August to 19th August, then the second week, the third week, which is 27th August, and the fourth week. So we see that it's all in the blue region, which means that the rainfall is likely to remain strong. And so even the next few days, next few weeks, there's unlikely event of a break happening. So we should be fairly safe as far as monsoons are concerned. So now I'll briefly talk about machine learning and the work where basically we use machine learning because it's a huge big data problem in some sense. We have huge amount of data collected from historical sources and also in today's world from satellites. And we use it in various fields, which includes climate change scenario to river basin scale, attaining good accuracy in predicting the mean Indian monsoon. And one of the first attempts we made for predicting Equino was with a machine learning process, and also identification and prediction of active and break spells. So this is some of the work that we have done. One of the things that we have done is using an autoencoder based identification of predictors and prediction of the Indian summer monsoon rainfall. This is a schematic, it's a single layer autoencoder. And it helps in discovering new monsoon predictors, initiates with grids over the entire globe, and each grid acts as input node to the encoder. And new monsoon predictors are a kind of a nonlinear combination of the input variables. So this is a schematic picture of the autoencoder based monsoon predictors. And from that, we have kind of identified some predictors, and the techniques which we have used includes the regression tree. And if we look at the accuracy, it is much better than the statistical models that are being used, with errors of about 4.5 to 5%, depending on which variable that we are using. And its skill is comparable. For example, this is from the dynamical model. While the encoder-based model with different predictors has about zero 0.8, around 0 0.8 is what we could say. Of course, numerical models are also improving, and their performance has also improved in the recent times. But what we can say is this autoencoder-based technique holds good promise for predicting the monsoon on the seasonal scale. And this is how it has kind of worked over different years. And when we combine variables, we find that it's pretty good. And even in April, when we are doing the forecast, the skill is quite good and comparable to what we get from other techniques. So this is the forecast for Indian summer monsoon from using the autoencoder method. We are hoping that we'll reach about 107%. Maybe the actual could be somewhere around 102 to 103. So yeah, you could say that it's going to be very close for us. And we also used stacked encoder based identification for early part of the monsoon, that is for June and July, and also for August and September, two different models for that, and also for different regions of the country. This is a schematic picture of that. And for, as I said, for four homogeneous regions, that is central, northeast, northwest, and southern part of the country. And that was a multi-level stacked encoder that we have used. And we use multiple layers so that because there are more complex features can be kind of abstracted at different levels. And the accuracy of them is pretty good. For the late monsoon, in India Met Department has a 7.8 error, but for us, the late monsoon error is about 4.9, which is better. And for the earlier part of the monsoon, the error is about 6.1. And we make predictions, or rather we have tried to make predictions. This is only an experimental work that we are doing, and predictions are made with a lead of at least a month. And these are more details of the accuracies of the regional monsoon, that is for the four homogeneous regions. And we find that for different years, x-axis here is different years, it's kind of working pretty well for using our stacked encoder technique. Other areas where AI and ML could be used, because it's, as I said, huge amounts of data from satellites and even numerical models, it's going to be a big data problem. Part of the numerical model is based on empirism, and that could be would be limited by a conventional understanding of and analysis of the data. For example, cloud modeling is one example where we, in the AI ML techniques, can abstract the process better and kind of be embedded into the model, the numerical model itself. And we are also making efforts to reduce errors in numerical model simulations by using AI ML correction techniques. And creation of better initial conditions for numerical models is also an area where AI ML could be used, and it's still a kind of an area of potential research. And forecast using AI ML could also be used for downscaling. That is, you kind of get information at a smaller scale, at a finer scale from an which is what IBM is trying with its new AI/ML technique, and directly forecasting on finer scales using observations. There are also efforts on for this, and of course, the efforts are still in a nascent stage. So this is an area of where a large amount of work could be done in an interdisciplinary fashion, where people from weather and climate could work with people with background in AI and ML, and we can kind of make better and better models, not just AI/ML, pure AI/ML models, but also the numerical models could be improved using AI and ML. Overall summary, we have seen that Indian monsoon is a part of the global system. It shows significant fluctuation within a season and includes active and break spells. We have northward propagation of cloud bands. We have seen that El Nino and Indian Ocean play a very important role in modulating the Indian monsoon. And there is an ambitious program called the Monsoon Mission Program, which has developed a dynamical forecast system, which is comparable to the best in the world. And as far as skill is concerned, especially for the Indian summer monsoon, I think it's about the best in the world. And as if you are coming to this year, then the monsoon should be good. there's a low probability of El Nino and a weak IOD. And as we just discussed, machine learning promises new areas of usage in weather and climate. So I think that's all I would have to say. And I would like to acknowledge my colleagues and friends at IISc as well as IITM. And I would especially like to thank my former postdoc, Dr. Momita Saha, who introduced me to the wonderland of AI and ML. And that's all I have to say. And if there are any questions, I will be happy to take.
Thank you, Professor. That was a wonderful talk. There are lots of questions actually. Yeah, so we'll just give a round of applause first.
Thank you.
Thank you very much. It's a great talk. Okay. So I'll take, are you ready to take the questions?
Yeah, I'll take the questions. Are they in my chat box or somewhere?
Actually, some of them are in the Q&A and some of them are actually in the chat and it looks like it's to the host, that's me, so I'll probably have to read it out. Yeah.
Yeah,
But
you
you
can
can
read
take the
out and
one in
I'll
the
try to
Q&A
answer.
first. Yeah.
Yeah, sure. So where do I see the Q&A?
Okay, I'll just, there's only one question in Q&A, so I'll just read it out. Is it possible to access the rainfall data statistics? Example, how much rain was there in 2005, 2006, 2010, 2012, etc. So,
Yeah, on larger scales, it would be directly available on the India Meteorological Department site from the entire period. All India rainfall, I think, is available from 1870 directly on the India Meteorological Department site. And also the gridded data at about 25 kilometers is also available, I think, on the IMD website. And if they need a particular station's data, then they have to, I think, write to the India Meteorological Department to get that data. But satellite data, etc., from especially from NASA at higher resolutions is also available, which is freely downloadable from the NASA. I think it's from the it's not GFDL. It's sorry, I forget it. But on the NASA site, you can easily get the data. And quite a few places, for example, Columbia University has a very good repository of climate and weather data, which also people can access and kind of download that data and use it.
okay. Okay, so now I'll go to Sridhar. Do you have any further questions? I have allowed you to speak. Okay. I think we'll go to the chat questions. Professor Devsagar has several questions for you. So
Okay.
he has said, what would be the impact of global warming on monsoons? As
Okay.
such, now the monsoon prediction is almost accurate. This accurate prediction is due to satellite data or due to models.
Okay, I'll take the first part of the question. That is climate change. It's still, you could say, an open question. There are competing effects happening in climate change. For example, if you're looking at just greenhouse gases themselves, because the atmosphere is going to warm, it is kind of likely to increase the strength of the monsoon. But then if we also take into account the particulate matter which is going into the atmosphere because of higher pollution, that is likely to reduce the strength of the monsoon. So there are competing effects. And in the short term, let's say in the last 10 to 15 years, we did see a weakening of the monsoon, which could be because of a large amount of increase in the particulate matter. But as we clean up the atmosphere, but the amount of greenhouse gases that we are going to put into the atmosphere is going to increase over a period of time. And that is likely to increase the strength of the monsoon. That's what most models are saying. If we clean up our act, then we may get a stronger monsoon in a changed climate scenario. And of course, how the greenhouse gases are going to change is still a matter of debate. And I hope we'll have more enlightened behavior from all of us to kind of reduce the impact of climate change. And as far as the improvement in forecast of monsoon is concerned, I would say that there has been quite a bit of work going on to improve the models and from all aspects, especially on modeling of clouds, which is one of the weakest links in a model. How we kind of put in clouds is a problem because clouds occur at a scale of 1 kilometer, and typically the finest model that we use is at about 12 kilometers. So we cannot resolve the models. the clouds, but the effect of clouds is very important. So we try to abstract the effect of clouds and put it into the model, and a lot of research is happening to this. This is called as parameterization, and that improvement has certainly improved our monsoon predictions. And of course, a large amount of data from satellites is coming in, which has also improved the initial conditions, and the technique to improve the initial conditions have also become more sophisticated using Kalman filtering and variational methods. So I think both of them are combining together to kind of give us better forecasts of the monsoon.
The next question is, like Lorentz attractor, is there any attractor proposed or constructed specific to monsoons?
There could be work happening at
Dynamic
different centers. Yeah, so for attractors, but we do find that there are cycles in a monsoon. For example, there are long periods when the monsoon tends to be on an average stronger, and there are also long periods when it tends to be weaker. For example, if we look at from 1920 to almost 1960, there were fewer droughts. And from 60 to about 90, there were a large number of droughts. And then again, we now, of course, anthropogenic climate change is also playing a role of a disruptor, sorry. That so there are epochs and there could be attractors, but I am not aware of it. And there could be work happening at various places, including TIFR, on the attractors of the monsoon.
Professor Saroj has asked, what is the best possible duration for forecasting the monsoon? As in, how ahead of time can you make a prediction that is the most accurate? How many hours or days by which earlier than the actual occurrence can you predict?
Okay. It's a tough question. Again, it depends on the spatial scale that you are looking at. Supposing you are looking at coarser spatial scales, the larger spatial scales, then we find that there is significant scale up to about three weeks. But if you're looking at, let's say, if you want a city-specific or an area-specific forecast, let's say what's going to happen in Bangalore, that I think the skill would be for about 3 days to 5 days. Beyond it, you may not have much skill. But if you, let's say, look at larger regions, then we can look at, say, there is likely to be an active spell or a weak spell, or there's going to be a hot wave or a cold wave. That we can kind of predict. But that would be over a larger region and not over a very fine region. So if you look at larger spatial scales up to about 3 weeks, you get very good signal. And if you're looking at all India as an average, then even a season in advance, we get reasonable skill for the seasonal forecast. So again, looking at the spatial scales, if you go to coarser scales, we get a longer period skill. And if you go to finer scales, spatial scales, then we get a weaker, shorter.
Temporary.
Yeah.
Professor Dayasagar again, what would be the impact of anthropogenic aerosols on monsoons?
Okay. Anthropogenic aerosols, again, there are two types of them. One is called as the absorbing aerosols, like the black carbon, which is what you get out of burning diesel. And then you also have sulfates. Now, if the aerosols are predominantly sulfates, which is what happens over most of the regions of the world, then these are kind of what we call as reflecting aerosols. That is, they reflect the sunlight away and they kind of just cool the atmosphere. So the effect would be to kind of cool the atmosphere and kind of reduce the heating in the atmosphere and hence kind of, in a sense, weaken the monsoon. But we also have these absorbing aerosols, which are more tricky to look at. And they absorb the sunlight which is coming in. They can heat up the atmosphere and hence can increase the strength of the monsoon. Again, over India, we have aerosols which are, but over the rest of the world, it's essentially sulfates. So again, what impact aerosols have, again, depends on the kind of aerosols we are going to have. And as we go to cleaner and cleaner fuels and better engines, sulfates may remain, but the black carbon certainly is going to go away, I assume, in the next 10 to 15 years. So, and of course, I'm hoping that aerosols themselves will reduce But of course, GHGs, the greenhouse gases are going to remain there for at least 100 to 200 more years. Their lifestyle cycles are very long. And we are emitting more and more of these greenhouse gases. So climate change is going to be there for a long time to come. We'll have to live with it, and we have to kind of adapt to it and use strategies to mitigate.
The next question is, how successful are mathematical and or statistical models in predicting the monsoons? There's actually a related question that is by Guru Datta. He's asked, over the past couple of years, there have been heavy rains in Kerala. Is this on par with the predicted model, or any changes occurring between the predicted model and the actual occurred rainfall?
Not just over Kerala, but over all parts of the world, we are seeing more and more of these extreme rainfall events. And that could be related to climate change. That is, the mean itself might increase or remain the same, but its frequency, that is, you may get fewer, more intense spells of rainfall. And those extreme rainfall events from climate change models, we know that, okay, that's kind of happens. And so the second part was about changes in the predicted model, is it?
Yes, yeah. Why do you see those? Is this on par with the predicted model, or are any changes occurring? Are there any changes occurring between the predicted and the occurred rainfall? So, do you see any
Uh,
discrepancies in the prediction model?
Prediction models, I mean, some of these extreme rainfall events might occur at a very fine scale, so we may not be exactly resolving them, but we do see a kind of a higher probability of higher rainfall events happening, even in our models. We have seen that, and we have been trying to predict it. And we are trying to improve the models so that we can get these high rainfall events much more better. One of them is to kind of go to a higher resolution and improve the models physics of clouds, which we are working on. And when we have moved from coarser resolution to finer resolution models, we find that our forecasts have improved. Of course, getting the right place and at the right time, the extreme rainfall event is a very tricky problem, because extreme rainfall event could occur for a few hours, and might happen at 2 a.m. while our model might say it will happen at 4 a.m. So, and then it will look like as if the model has gone wrong. But if you look at larger averages, we are able to capture some of these extreme events, and it's a tough problem. And we are working on it to improve the prediction of these extreme events. And they are likely to happen more and more in a changed climate scenario.
Okay. Next question, what is the possible accuracy of the long range forecast for monsoon rainfall issued by IMD?
Okay, I think I showed those numbers. It's about, I think, 5 to 8%, right? So, sorry, let me just go back and. Yeah, these are the error. The model error is 4% for the second stage with 102%, and 100% with a forecast error of 5%. These are the errors in IMD forecasts.
Next question, tropical and subtropical regions are going to have lesser and lesser rainfall, whereas the polar regions are getting more and more rainfall, wet getting wetter and dry getting drier. Are these statements valid?
Well, I mean, polar regions are getting warmer at a lower rate. So their moisture holding capacity and hence rainfall could happen to be increasing. And if the equatorial regions, if the rainfall is increasing, then the mid latitudes could get drier, because as we saw, there is the Hadley cell where the dry air descends over the mid latitude. It's possible that that could happen, but we are not sure. There are huge uncertainties in these model scenarios, so it's difficult to say that okay, this is likely to happen, but it might happen. And of course, the sea ice is going to melt, so the reflectivity is going to change a lot, and that can also have an impact on the radiative balance of the atmosphere, especially in the higher regions. So it's a tough problem to say that, okay, this is exactly going to happen. So
Seems like a very delicate system, right? And very complex also. It's pretty interesting.
yeah, it is. It's one of the toughest systems to study.
Work with, yes. Yes, so the next question by Gurudatta is it possible to harvest all rainfall and thus recharge the rivers? Is there any
Uh,
safe and room for harvesting is what I guess he's asking. Should we all be doing that?
In theory, of course, we can do it, but
Right.
there are also ecological impacts. For example, if a river is flowing naturally, it also has its own ecosystem. So I would not suggest that we should harvest all the water that is falling as rain. Some of it has to go into the, let's say, to the ocean. It has to flow. So I think a large amount can still be harvested and harvested in a kind of ecologically sensible fashion rather than building huge dams. We have more check dams and which kind of also reduces the amount of floods. Then I think should be done, but I don't think we should harvest the entire amount of rainfall that's happening because, as I said, fresh water also plays a role in the climate system. For example, over Northern Bay, if you kind of remove that high fresh water, it could affect the ecosystem as well as the climate system. So some amount we should still allow, some amount we should harvest it, and of course use it in a more economical fashion.
Okay, this is a question from Mohammed Asad Ansari. He's asking up to how much extent the rain on other regions affect the Indian region. Is there any relation that shows rain in one region makes a lot of, if it affects the Indian region monsoon? So are there effects from some external climate system that affects monsoon is what he's asking.
Yes, it does. As we saw, let's say if there is more rain over Central Pacific, we do have an ENSO kind of a system occurring there, and so happening. And when that happens, the Indian monsoon is likely to be weaker. And also, let's say if there is more rain happening in the eastern part of the Indian Ocean, that's likely to kind of reduce the strength of the Indian monsoon. So there are other regions of the world where if there is more rain or less rain, that kind of affects our Indian monsoon. As we saw, it's part of the global system. So if one part gets perturbed, or the system gets perturbed, it's going to affect the other part, and Indian monsoon also gets affected by the same.
Yeah, so now I have two questions and I guess I'll close that. So the first question is you mentioned about the spatial scales, right? So what are the different scales that you have when you go from finer to the coarser? Like, is it in terms of the area it covers, or is it like a city and then a state, country, continent, that sort of scales? Or when you said spatial scales, what did you refer to?
Okay, it's basically spatial in the sense of the size of the area that it covers. For example, if you're looking at a cloud, a typical individual cloud, that would be of the size. Its horizontal scale would be about 1 kilometer. Its vertical scale could be, let's say, if it's a short cloud, it could be a few kilometers. If it's a tall cloud, it could go up to 10 to 15 kilometers. And then there could be a cluster of such clouds, which we call as the mesoscale convective systems. Larger than that could be some sort of a cyclonic system or a depression or a low, which could be of the order of hundreds of kilometers. And then we have the planetary scale systems, such as the Indian monsoon and also ENSO, and then a much larger scale, like the ENSO monsoon teleconnections and all. So there are various spatial scales, and they have time scales kind of related to them. For example, a cloud will live for about a few, at best, minutes to hours, while the monsoon lasts for about 3 months, and then a depression lasts for a few days. So there are various temporal and spatial scales that are interrelated to each other.
Okay. The other question I have is like, how do you, so the education, higher education ecosystem, right? So, what kind of skill set do students need to start working in these complex problems, right? So, do they, and what kind of students do you get, right? And if you have to attract more students, and I think monsoon is a very pertinent problem for us, and considering this so important that we should have so many more students working on things like this, right? So, what is your thought on that?
I think any person with an interest and having a reasonably good scientific and mathematical background
Mm.
can work in this. Like
Okay.
I and many of my students started as engineers and then moved into atmospheric science and into monsoon prediction. And the
Okay.
fact that as mechanical engineers we understood fluid mechanics and thermodynamics helped us.
Okay.
And of course, we need mathematicians who can look at new techniques to analyze. And of course, these days with
Data scientist.
AI and ML, so computer science or computational science students can also look at it. And in IISc, when we look at monsoons, we have to get students from all backgrounds who
Okay.
work with us, and we train them in atmospheric science and ocean
Okay.
sciences, and of course climate. And from there on, they take off. And
Okay.
like I have had a couple of postdocs who were in from the computer science background. Like I got
Okay.
introduced to AIML from one of them.
Right.
So
Sure.
yeah. So I mean, we need people from various diverse background, and not only that, we need people from with high performance background, computing skills, because these models are highly demanding as far as computational resources are concerned. So we need to
Correct.
make them as optimal as possible. So from all a diverse background, we need people who can work on
Right.
it. And I would say that there's a severe shortage of good skilled people who can look at this tough problem. And everybody is welcome to chip in and look at it from various
Def-
points.
Definitely.
Mhm.
So, will you show your camera now first before
Oh,
we
okay,
close
sorry.
the session?
Sure.
That'll be great. Yes. So then we can formally thank you for such a wonderful talk.
Okay. So I'll stop sharing. Let me see, how do I do that?
There will be a video camera icon there, so we can.
Okay, yeah.
Okay. Thank you so much, sir. The Professor Dayasagar has also mentioned this is a remarkable talk. Thank you, Professor Ravi. And on behalf of IEEE GRSS Bangalore section, we are really grateful to you for making it here and giving such a wonderful talk. Saroj, would you like to say some more?
Yeah, it's a great talk, and it's an honor for us that you agreed to give a talk for us. And we hope that in future we may seek your suggestions and your advice, because we belong to GRSS society, and we will be dealing with all these kind of activities in our day-to-day activity. So many students normally used to come to us, and they sometimes, because we are not domain experts, so we may seek your expertise in that, and we hope that we will be getting from you, sir.
Sure,
Thank
I'll
you very much.
always be more than happy to help out, and it would
Sure,
be a
sir.
pleasure. And it's a
Thank
pleasure to be here. I mean, virtually, of course, but
you.
it's a
Yes.
pleasure for me to give this talk. And I appreciate for organizing this talk. Thank you.
Thank you so much, sir. And yeah, happy
Thank you.
Independence Day to everybody.
Yeah.
Yeah, I also wish
Thank
everybody a
Thank
happy
you.
Independence Day. Though it's not in the nicest of conditions, but whatever it is, I think we should,
you. We'll still celebrate.
yeah, be happy with it. Yeah.
Yes.
Okay.
Thank you so much, sir.
Thank you, sir. Thank you.
Yes.
Thank you.
We'll
Thank you.
see
Good
you.
night.
Bye. Good night.
Good night.
Okay. Good night. I can end the call now.
Okay.
Yeah, thank you
Bye.
so much. Bye.